Okay, good afternoon. Midterm Wednesday, review session Sunday. I think that's all under control. What we're doing today is looking at an example program, which is a little four-function calculator. And we're looking at this program for two reasons. It says up on the board. First is it's an example of processing deep lists, that is, lists of lists of lists. Because in this calculator program, I can say plus times 3, 4 times 5 plus 6, 7, as deep as I want to go, and it'll figure out the answer. So if you look at that expression as a scheme expression, it's exactly like what you've seen before, but now I want you to look at it as data, and it's a list of lists of lists in some cases. Okay? So we are looking at how to handle such a situation. And great t-shirt. You. Also, down the road, we're going to be looking at a scheme interpreter written in Scheme. And traditionally, this has been a big obstacle for students. It's sort of all of a sudden we're looking at this big, complicated program. And so we now build up to it in little steps, and this is our first little step. So unlike an actual scheme interpreter, this one has no variables, no procedures as first-class things. In fact, it only has 4 procedures you can call altogether, plus, minus, times, and divide. But it's scheme-like in its notation. So you say, plus 6, 7. You don't say 6 plus 7. And it does composition of functions in exactly the way that Scheme does. So although this is very, very, very simplified, most aspects of it are pretty realistic. And the big overarching picture that I want you to get is up on the third board. It's that there are 3 pieces to an interpreter. It has a Y in parentheses there because it's any interpreter, not just a scheme interpreter. Basically, any interpreter for any language is going to have pretty much the structure that you're about to see. And there are 3 parts to it. The first one is a very simple part. It is this, the read-eval print loop. If you're a Lisp person, you say REPL, and everybody knows what you mean. You mean this. It's a loop because the last thing in it is a tail call to itself. So this runs forever. And it's a read-eval print loop because of this line. And remember that things in Scheme happen kind of inside out. So when Scheme sees this, first it calls the read procedure. And the job of read is to turn things with parentheses into basically box and pointer diagrams, into pairs. So the read procedure gets this example like this as just a string of characters, and it looks at them and says, oh, this is an open parenthesis. That means this person is starting a list, and so on. And it creates the box and pointer diagram the same as you should be able to do. And then the result of read is given to eval. It's actually called calc eval so that it doesn't get confused with eval that's an actual STK primitive. So this is calc eval, but it's the evaluator, the core of the evaluator, and it takes an expression as its argument, and what it returns is the value of that expression. And what do we do with that value? We print it. We call print. So that's why you actually see a 77 there. So read read the expression that you typed, eval calculated the 77, and then printed 77. Okay? So questions about the REPL? Great. Easy, right? This is the easy part. Eval's not so bad either. It's pretty small. It's small partly because of the restrictions on what kind of expression we can have. So in scheme, there are basically 4 kinds of expressions. And they are self-evaluating, which are things like numbers and Booleans. Right? You type in number sign t, its value is number sign t. You type in 23, its value is 23. Those are self-evaluating, which we have in the calculator, namely numbers. There are variables, which we don't have in the calculator. So that's a complexity left out. There are function calls, which we have. They're limited to 4 functions, but they're there. And there are special forms, which we don't have. And when we look at an actual scheme interpreter, we'll see that a lot of the complexity goes into the special forms in eval. So this eval is just a 3-way con clause. If the expression is a number, then we return x, which is the expression. So the expression is its own value. That's why it's called self-evaluating. If it's a list, then it's a procedure call. That's what a list means, call a procedure. And we're going to call calc apply, which I'll talk about in a second, to actually apply that function to arguments. If it's anything other than a number or a list, it's a bad expression. It's an error. Okay? So every list is a procedure call because there are no special forms. So this is a very, very simple version of eval, but something like this is at the heart of every evaluator, because what's an evaluator's job? It takes the stuff that you type in and figures out what that stuff means. And that's eval's job, figuring out what the notation means. If we were writing an interpreter for a language like Java, eval's job would be way more complicated because there are a bazillion different notations and they're not uniform, and what you can put in one context is different from what you can put in another context. And so eval is really, really complicated. In Lisp interpreter, eval is much simpler, partly because one complete expression is one list. Okay, so the form of expressions matches the form of the data that the language knows how to deal with. So language was designed in order to be able to evaluate its own programs very straightforwardly. And this is why Lispians say, at the heart of every programming language, there's a Lisp interpreter trying to get out. Because basically what you have to do is evaluate expressions that are mostly procedure calls and a few other things. And it's just that there's a lot of syntax in the way of doing that. So here the syntax doesn't get in the way. All right, so we have a very simple eval, but it's not totally simple because right in here, there's something that is much more complicated than it might look. It's sort of a recursive call, but it isn't a recursive call exactly because there's no open parenthesis in front of calc eval. Instead, we're using calc eval, which is this procedure that we're in the middle of, as an argument to map. Map is going to call calc eval typically more than once, right? However many sub-expressions there are, however many arguments there are to your operator, we're going to call calc eval once for each of them. So in this expression down at the bottom, we called calc eval on this whole thing. Calc eval says, okay, first thing I have to do is call calc eval recursively for times 3, 4, and also call calc eval recursively for times 5 plus 6, 7. Now, the call for times 3, 4 has to evaluate 3. That's a trivial job, but it has to be done. We have to recognize that this is self-evaluating, and we have to recognize that 4 is self-evaluating. We have to recognize that 5 is self-evaluating, and then we have to say, oh, look, here's another list. So that means another call to calc eval for a function call, and for that one, we have to evaluate the 6 and the 7. Okay? So that's a total of 1, 2, 3, 4, 5, 6, 7, 8, 9 calls to calc eval to compute the value of this expression. Okay? So this call to map here is more than just a simple recursive call. It's a multi-way recursive call. And this is the secret to dealing with deep lists right here. That if you have a data structure that's a list of lists of lists of lists to whatever depth you want, then to deal with it, you have to make a recursive call for each element of the top-level list, and then for each element of sublists, and so on, all the way down. So what's the base case for this kind of multi-way recursion? Well, it's the base case of map, which is what? What's the base case of map? Yeah. Yeah, empty list. Okay, map, some function, empty list. Just returns an empty list. Okay? So that's one base case for this process, is that we've evaluated all the arguments. So map is given, 3 arguments or something, and it did a recursive call for the first one, recursive call for the second one, recursive call for the third one, and oops, I have an empty list, finished. Okay, so that's the base case. The other base case is right up here, where if the expression isn't a list, there's no recursion. It's self-evaluating. Okay, so that's 2 kinds of base cases. The way you can think about it is the map base case, think of as being sort of horizontal. You had this expression, this expression, this expression, and you reached the end. And the number base case is like vertical. You've done a recursion and then a recursion inside that and a recursion inside that, and now we're looking at 3. We don't have to do any more recursive calls. But that doesn't mean when we get to this 3, that doesn't mean that the whole problem is solved. I'm betting that despite our discussion about recursive versus iterative processes, a lot of you have in your head the notion that when you reach a base case, everything is finished. Okay, that's not the case here. When you reach this base case of the 3, we aren't going down any further, but now we have to look at the 3's sibling, the 4, and then we pop up and take care of the times 3, 4, and now we have to look at a 5. And so there's a lot of work still to be done when we reach the 3. Even when we reach an end of list base case, so when we've processed the 3 and we've processed the 4, and now we come to the end of this list, that's a base case for map, but we still have this piece to deal with. Okay, so base case doesn't mean the whole job is over. It just means we're not doing any more recursions down this particular road. Okay? Questions about that? Yeah. How does it know to call calc when it sees the plus sign? Oh, thank you. I messed up. Oops. No. Oops. There. It knows because it's not schema, it's in calc. Thank you. Good call. Hard day. Okay. So what's the second argument to map? It's cdr of exp. And this is, we're getting toward one of the ways, well, the principal way, actually, in which the calculator is different from a real scheme interpreter, which is we're not going to see a recursive call for car of exp. Car of exp has to be one of the four symbols, plus sign, minus sign, asterisk, slash. And we're going to use that to represent the function in the call to apply. In a real scheme interpreter, it could be a symbol that's the name of a procedure, but it also could be a lambda expression or another procedure call that returns a procedure, or all kinds of things to provide the function. So we have to eval the car also, but here we're not going to. We're only evaluating the elements of the cdr, which are the arguments to, in this case, plus. And then we're going to call calc apply with two arguments, namely a symbol, plus, minus, slash, asterisk, slash, right? And a list of actual argument values. Okay, because cdr exp is actual argument expressions. Right, so cdr exp looks like this. But map calc eval cdr exp, the result of that is the list 12 and whatever 5 times 13 is. 65? 75? Something like that. No, 65. So the list of two numbers, which are the actual argument values. So this structure, in which we recursively evaluate the arguments before we call apply, is the implementation of applicative order. Got it? Applicative order means first you evaluate the argument expressions and then you call the function. And that's what we're doing here. If we took out the call to map and just called calc apply with car exp and cdr exp, we'd be doing normal order evaluation, where we give the actual argument expressions to the function. Okay? So this is I'm sort of obsessing on a small point, but there's a meta point that I'm making, which is that by reading the code of an interpreter, you can really see the answers to the questions of, what is the language that this interpreter interprets. And here what we're seeing is that the language is applicative order because of this way the call to calc apply is done. Any questions about that? Okay, who's with me? Thumbs up, thumbs down. Okay, so all the people who aren't voting, is that thumbs down? Come on, I want to see every hand up. Thumbs up, thumbs down. Every hand, you too. Okay, a couple of sidewayses, but it's not too bad. All right. So just for the sideways people, let me say it once more, and then we'll move on. There are a bunch of different properties of a programming language that determine what it is to be a program in that language. We've looked at a bunch of properties. So one of the properties of Scheme is it has first-class procedures. Another property of Scheme is, it's applicative order. And another property of Scheme is it does have variables, and so on. Okay? Lots of different things that make Scheme Scheme. And every one of those things manifests itself in the interpreter. So we can look at the interpreter and ask questions like, how would I change this interpreter if I wanted, just like Scheme, only normal order? Right? And the answer is, you would not call map in here, but just use cdr exp as the second argument to apply. And then we would be giving apply actual argument expressions rather than actual argument values. Okay? Which is what normal order means. Actually, I'm saying this with my fingers crossed, because in a real language like Scheme, it's a little bit more complicated how normal order works, and we are going to get to that. But basically, this is applicative versus normal order right here. Okay, so we call apply with exactly 2 arguments. The first argument is the function that we want to apply. Apply is, a fancy name for call a function. And the second argument to apply is a list of argument values. Even if there's only 1 argument or no arguments, it's always a list. And that's so that it has a uniform definition. So function, arguments. And in the definition of calc_apply down here, you see that it takes function and arguments as its arguments. Okay. Here's the place where the calculator program diverges from what Scheme does. It's not just a simplification, it's actually a difference. And that is, in actual Scheme interpreter, it's the procedure itself, because procedures in Scheme are first class. So that function argument would be the procedure that adds numbers, or the procedure that subtracts numbers, or the procedure, etc. In this calculator, we don't have procedures as first-class values, which is a big simplification. And so instead, the first argument to apply is the symbol that names the function we want to use. So it's the plus sign or the minus sign, etc. It's a little bit like the distinction between applicative and normal order, except that instead of being about the arguments, it's about the operator, the function that we're calling. And we give the name of the function rather than the function itself, because there's no way to represent that in our calculator. In a week, we're going to look at a still somewhat simplified Scheme interpreter that does have first-class procedures, and you'll see how that works differently. So this calc eval is actually a little more complicated than the real one, because it has a cond with 5 cases. Is this plus, is this minus, is this times, is this divide, else error. Okay? So that means if I say something like, square root of 4, I get bad operator, square root. Okay? And that call to error, by the way, I guess we haven't explicitly talked about this. Error is a Scheme primitive that prints an error message and gets you back to the Scheme read eval print loop. Because STK is an interpreter just like this. STK has a REPL and an eval and an apply. Just the same as this, except for Scheme instead of for the calculator language. So we really are looking at something pretty real here, except for this business about 4 different con clauses for 4 different operators. So plus and times are easy. We treat all the arguments the same way. Minus and divide is a little more complicated. We can't call them with no arguments. If we call them with 1 argument, then we return either the additive inverse or the multiplicative inverse of that one number. So either minus car of args. So if there's only 1 argument, args is still a list, and the 1 argument is car args. So here I'm taking the additive inverse, minus car args, and here I'm taking the multiplicative inverse. Divide, real Scheme divide does the same thing. So this is like saying 1 divided by car args. Okay? Otherwise, what Scheme does, Scheme actually allows multiple arguments for minus and slash, even though it's kind of silly. And it treats the first one differently from all the other ones, basically. So it takes the first argument minus the second argument, that result minus the third argument, that result minus the fourth argument. So the way I represented that here is take everything except the first argument and add them all up, and then subtract that from the first argument. Probably would have worked to let Scheme handle this, but I'm making explicit what the semantics, the meaning of minus and slash actually are for these funny cases where there's multiple arguments, more than two. 2 arguments is straightforward, but this handles 2 arguments also. Okay? Questions? Yes. What's the point of the 1 or the 0 in the accumulate procedure? Accumulate takes an accumulator function, like times in this example, and a base case value. So what's the starting point for the accumulation? So it starts with, in this case, 1, and then it multiplies that by the first argument, and multiplies that by the second argument, and so on. Does that answer the question? Yeah. If you took CS3L, you may have seen a version of accumulate that doesn't have an explicit base case argument, and instead you have to call it with functions it knows about, basically. It has a bunch of base cases built in. Okay. Any more questions about apply? Yeah. Yeah, if I say paren star close paren, indeed I get 1. And that's because if you call accumulate and args is empty, it just returns its base case value. Isn't that bad? No, why? Yeah, this is what Scheme does. If you call times with no arguments, it's a slightly funny thing to do. But if you do it, the identity element is the right thing to return. Should I convince you of that? Is that, or do you believe it? Head shaking. All right, it won't take very long. I'll convince you. Oops, now let's use this one. It's cleaner. Okay, no, even better. Okay, the value of this is 60, right? Okay. I'm going to cross off the 5. Now the value is 60 divided by 5, which is 12. Yeah? I'm going to cross off the 4. I'm going to get 12 divided by 4, which is 3, right? Now I'm going to cross off the 3. So in order to behave consistently, it has to return the identity element. Nobody ever calls it like that, open paren, star, close paren. But what does happen is people call apply, multiply, to a list of arguments that happens to be empty. Yeah? Why not trigger an error? It's not an error, mathematically. Ask a mathematician. Any mathematician who's never seen Scheme before will predict that behavior. Yeah? Oh, sorry. Good question, but badly timed. He's asking, what's this flush here? This is a little stupid operating system thing. Every operating system, basically, when you output text to be displayed, it doesn't actually do the displaying until you output an end-of-line character. So it puts up a whole line at a time. In the case of a prompt, we want to print the prompt and then sit on the same line. So the flush procedure says, even though I haven't sent you an end of line, put this out anyway. Okay? That's what it means. Yeah. Other questions? Okay, let's see what I haven't said yet. Oh, yeah. While we're back here, read and print, they're primitive procedures, and they're not functions. They're not functional. Read is not functional because every time you call it, you get with the same arguments, namely none, you get a different answer, right? So that doesn't satisfy the definition of a function, which is that your answer shouldn't depend on anything except the arguments. And print is not functional because it changes the state of the world. Namely, it changes what's up on your screen. Okay? And anything that does that is not functional. Functions just compute and return values. So even though we're doing functional programming in Scheme, the Scheme interpreter itself is not entirely a functional program. However, the guts of it, eval and apply, are functional. Those things, all they do is they take arguments and they return values, and you can predict the return value from the arguments, except for the fact that you can define variables. Okay, so that's a little bit of non-functionality in evaluating expressions. But these eval and apply, the ones in the calculator, are totally functional because you can't define variables. So the state of the world doesn't affect what they return. So that's an interesting little bit of trivia. Read and print themselves are slightly messy. You know, you have to say, okay, let me look at the next character. Is it a quotation mark? Do this special thing. Is it a space? Do this special thing. Is it an open or closed parenthesis? Do these other special things. And otherwise, sort of accumulate characters until you get to a space or parenthesis. And then look at what you've got. Are they all digits? And so on. So it's not a huge intellectual leap the way, higher order functions probably were for you. But it's messy and has a lot of detail to it, and we're not bothering to look at it. We're just taking it as given because it doesn't really repay the effort to read it. But you could read it. You could write read and print in Scheme, given the primitives, the more primitive primitives, read character and print character. And read and print work in terms of those. Okay. A little piece of vocabulary. Syntax is the technical term for the form of a program, what a program looks like. So Scheme syntax is open parenthesis, procedure, argument, 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 close parenthesis. That's what a function call looks like. Semantics is what that thing means. So open parenthesis, blah, blah, blah. What that means is call this procedure with these argument values after you've recursively evaluated the argument expressions. Okay? So if you look deep enough, programming languages, I was about to say all programming languages have the same semantics. That's clearly not true. Some programming languages, for example, are in normal order. I mean, real programming languages that people use. Some of them are like that. But more or less, you're going to see the same kinds of things in the semantics of every language. You're going to see some way to make a conditional decision, something like if or cond. You're going to see some way to have a loop, like a tail call. You're going to see some way to call functions. You're going to see some way to define variables. All of those things, they're the same kinds of categories of meaning. The syntax of different programming languages is very, very different from each other. If you've studied another programming language, you'll know that. If you took CS10 last semester, the syntax of the language you used was all full of pictures instead of text. It's very, very different. But if you studied Java in high school or community college or C++ or something, that looks much more different from Scheme than the meaning is different from Scheme. Okay? So syntax and semantics, piece of vocabulary there. Big important point. We are here dealing with two different programming languages. Okay, the calculator is a program written in Scheme. The language that the calculator implements is a programming language, a really trivial one, but a programming language, that isn't Scheme. Okay? So when I say, for example, that there are no variables in the calculator language, right? So if I say, foo, that's an error. If I say plus sign, now let's be clear about this. If I say plus sign in parentheses, that's 0. If I just say plus sign, that's an error. The error message is bad expression, plus sign. Okay? That wouldn't be true in STK. If I say plus sign, I get a value back. It's the addition procedure. Okay? So two different languages. Up here, we have variables. We have, for example, here's exp is a variable. So even though the calculator language doesn't have any variables in it, if I type exp into the calculator program, error, bad expression. But I can type exp into STK, and, well, if I do it right now, I'll get an error message also because the variable is local to calceval. But I can say calceval, that's a variable, and its value is a procedure. All right? So two different languages, two different prompts. There's the STK prompt, which looks like that, and then there's the calc prompt, which looks like this. Okay? These languages are different enough that I don't think any of you is going to get confused about this point. So we can't write, for example, an if expression or a cond expression in calc language, but we can use cond, as we do up on the screen here, in Scheme in defining what the calculator language is. Okay? I'm belaboring this probably obvious point because pretty soon we're going to be looking at Scheme interpreters written in Scheme. And that's going to make it a little more confusing. So I want you to get this point clear in your head while the languages look pretty different from each other, that when you have a Scheme interpreter in Scheme, there are two languages involved. There's STK Scheme, and there's my Scheme interpreter Scheme, right? And they're going to be a little bit different from each other. So we didn't implement every single feature of real Scheme in our interpreters. We just took, the ones we thought were important. And so the languages are different, but they look very, very, very similar. And so if we allow, for example, cond expressions in our Scheme interpreter, and if the procedure that implements cond expressions uses a cond, many of you are going to think the first time you see that, oh wait, this is cheating. Right? How can you use cond to define cond? And the answer is we're not cheating at all. We're using STK cond to define our interpreter cond. Okay? So try and keep that straight while it's simple as preparation for the next big step. Okay. Another thing about eval and apply, and this is why I brought up syntax versus semantics. Eval lives in both of these worlds. In a sense, eval is the program that turns the syntax into the semantics. It knows the form of a program that you type, and it turns that form into something meaningful that's a request to compute some value. Okay? So it takes an expression, a piece of syntax, as argument and returns a value. Apply doesn't know anything about syntax. And this is why apply is separate, a whole separate thing from eval when we think about it. Because the two arguments to apply in the real interpreter are a procedure and argument values. So it's not the notation for a procedure. It's not like lambda blah, blah, blah. It's a procedure and values that it takes. So it's all in the world of values. Its work is entirely about semantics and not about syntax. So any piece of syntax that's in the language is going to be taken care of by eval. Except for, I should say, the pieces of syntax that are handled by read, which is mainly the parentheses, but also quotation marks. Okay? Oh yeah, one last thing. Okay. Yeah, it isn't true here. Eval calls apply right here. Right? When we get to an actual scheme apply, we're going to see that apply calls eval. Think for a moment about why that's true. Back to scheme now. What does it mean to call a procedure? It means compute the actual argument values, substitute the actual argument values for the formal parameters in the body, right? And then evaluate the resulting expression. So when you call a procedure, eval is going to end up calling apply. So this is eval and apply calling each other back and forth. And that's a pretty complicated control flow. If you try to draw one of those diagrams like they did for Fibonacci numbers with trees and arrows going up and down and everything, it gets pretty complicated. And it needs to be complicated because of the complexity of deep lists as a form of expression. Right? So when you have a list of lists of lists of lists, and so each of those, so what that is a function call that involves function calls to compute the arguments, and those things involve more function calls, and so on. You need this thing that's called mutual recursion to handle it. Mutual recursion is going to be a big part of what we look at next week when we talk about trees as a data type. So I wanted to leave you with this sort of preview of coming attractions. And we'll see it in the scheme interpreter at the end of next week. Any last questions? Going once? Ah, yes. Wait, hang on, stop. Okay, syntax and semantics. Okay. His question, and it's a good question, so don't be in a hurry to leave, is why doesn't apply care about syntax? Because syntax is important in function calls just like semantics is. So here's why. Okay, here's a scheme function call. Here's the same thing in almost every other programming language, right? Right? Here's another procedure call, function call, f of 3 and 4. And in almost any other programming language, it's f parenthesis 3 comma 4 close parenthesis. Okay? Does apply know which of these things you typed? No. Apply knows that you want to call the function f, and you want its argument values to be 3 and 4. Okay, that's what we tell apply. Getting from this string of characters, open paren f space 3 space 4 close paren, or f paren 3 comma 4 close paren, getting from that to the arguments to apply is eval's job. So eval takes this semantic stuff and gets rid of it. So we're left, this syntactic stuff and gets rid of it. So we're left with the semantics of calling a function. Does that answer the question? Okay, great. See you next week.